And we're going to continue talking about naming ketones. So we have an example here. And then I'm going to talk about what to do for your ketone in one compound. So we have this compound, we have multiple functional groups. Notice we do have two ketones, so we want to try to get both of them in the parent group. And then the other functional groups as well, and if we get both of the ketones in the parent name, those other functional groups are going to be in there. But our ketone is going to be our highest priority. So our parent is, of course, going to contain both of the ketones. And we want our two ketones to have the lowest numbering system possible. And then the other functional groups will fall into place. Now, if numbering from either way gives the two ketones the exact same numbering system, then you can look at the other functional groups. But in this case, if we number from one way, then this would be on 1, 2, 3. But if we number from this way, our first ketone will be on 2. So our lowest numbering system would be numbering from that end. Of course, we have a propyl group, and since we have our ketones that we're naming for the parent in our double bond, we'll just put our alcohol as a side chain, a hydroxy. So just putting that together, remember alphabetical, H comes before P. And this will be our best numbering system because our ketones, carbon, will be on 2 versus 6. If we number from the other way, it would be 3 versus 7. So 2 versus 6 is the lowest numbering system. Remember, don't number the oxygen as number 1 for that alcohol. It is not a carbon, so we only number carbons in our parent. So our correct route is the route in blue for our numbering. Now in this case, because we have an ene and a dione, we have 2, so of course we have to specify that by di. It's probably a little bit better to put your locate numbers here, just for clarity. Even though a reader should know that priority takes the diones, but just for clarity, we'll put the numbers right before. If we didn't have this ene and it was just octadione, then putting it in front would be fine. So our hydroxyl is on 1, our propyl is on 5, our ene starts on 3, we only put that first number, and then our diones are 2 and 6. So this is our full name. Now, if there is any stereochemistry that is specified, we would write it. And we do have our double bond, and it does have an EZ isomer. So we do want to include that, and that'll just go in front of the name E, because we know that's for the double bond. Our two highest priorities are opposite, 1 and 2. The other two things are H's. H's are never going to be as high a priority. Now, technically, carbon 5 is a stereocenter, but geometry is not being specified, so we can't name it because we don't know what's going back and forward. So it's just going to be assumed that that particular compound is a mixture of stereocenters. But if the geometry is specified, we could name that stereocenter as well. Carbon 1 is in the stereocenter. So you answered this one, but I'll let you answer it again. So for this one, we want our longest numbering system that contains our ketone. So that is going to be this numbering system. That'll be 8. If I go the other way and use this and this, that'll be 8 as well. So it's kind of irrelevant. But the ketone is part of it. Though the longest carbon chain continuous is actually 9, it doesn't contain the ketone carbon. So that's not going to be our parent. And then, of course, we want our ketone to have the lowest numbering system possible. So our numbering system should have that ketone on 2. It doesn't really matter where the butyl group is. That's 4, so that's butyl. So this is 4-butyl, 2-octanone. And also notice, because this is an N, we do keep the A. just with the ohm. So for octane, it's octanone. But that's just a small detail. If there is an aldehyde and the ketone in the same compound, what do we do? What do we put as priority? So that's something we have to talk about because those carbons have the same oxidation state. So as far as priority-wise, we're going to try to include both in the parent chain, if that's possible. And our aldehyde's going to take priority, replacing the E with Al. So our aldehyde's taking priority, and our ketone is going to be a side group. When our ketone, and really that aldehyde carbon is going to be number 1, so it's not necessary to include the locate number because we know it's going to be at the end. And then the ketone is going to be represented with an oxo right before the parent name. So that's not alphabetized, it's just right before the parent name. Representing the ketone and representing the aldehyde is after the parent name. And that one has to have a locate number because that carbon-oxygen double bond can be on carbon 2, 3, 4, 5, or 6, so we have to specify where it is. So for this example, our longest chain is 7, so it's heptanol, and then our ketone is on 5, so it's 5-oxo. And this is always kept with the parent. So the oxo doesn't get alphabetized. If there's other other substituents, they just go in alphabetical order before the oxo parent name. So that's how you name it if you do have both a ketone and an aldehyde. You have 2 ketones, it would be dioxo. 3, trioxo. And again, all those locate numbers. So that's only if you have those 2. Pretty much aldehydes considered your main functional group just because we know it's always on. Because there's no difference in oxidation state. So that's our priority. So let's talk a little bit about reactions. First off, how to make aldehydes and ketones. We've talked about a lot of different reactions that form aldehydes and ketones, so we're going to review those. And none of these are new. So we know that if we take an alcohol that's primary and we use our oxidizing agent PCC, we can form an aldehyde. No difference in the carbon-containing group, nothing like that, but we just get the aldehyde. We have to use PCC, otherwise it doesn't stop. If we use a carbon-carbon double bond that has 2 hydrogens, then when we do ozonolysis, that'll break that carbon-carbon double bond, we form a CO bond O's. If they had hydrogens on those carbons, then they're going to be aldehydes. This reaction is really only useful if we're opening up a ring, or if we have a very symmetric double bond, so we form 2 of the same aldehyde. Because if we form 2 different aldehydes, then we have to separate them. So that's not typically as useful. But it can be useful, especially if we have a double bond in a ring and we're opening up the ring. So then we have 2 aldehydes on each side. If we do hydroboration oxidation of a terminal alkyne with a triple bond, then we get an aldehyde because we get the anti-Markovnikov addition. Again, this class really builds on itself. We've already talked about a lot of these functional groups. As far as ketones, if we do oxidation of a secondary alcohol, we form a ketone. If we do ozonolysis and our carbons have 2 R groups instead of a hydrogen, then we form the ketone. Again, only really useful if that double bond is symmetric, so we form 2 moles of the same ketone, or if we're opening up a ring. If we take a double bond and we react it with a triple bond, and we react with H2SO4, H2O, and HCSO4, then we can form our ketone. Again, notice none of these, we're not adding any carbons. We're just starting with some sort of functional group and converting it to a ketone, or an aldehyde. So this is our Markovnikov addition. So what results is a ketone. And then the last one for a ketone is, specifically if we take an aromatic ring and we do Friedel-Crafts acylation, we form a ketone where 1 R group is our benzene ring. That one's very specific. That reaction only works with an aromatic ring. Most commonly benzene, other aromatic rings it can work with. In lab, we do ferrocene. So we actually do a very similar reaction. So all of these form ketones, all of those form aldehydes. None of those are new, and you should know those. So we already know a bunch of ways to make and prepare aldehydes and ketones. Now let's talk a bit about aldehydes and ketones and really dissect their functionality. And the way you should always look at a functional group is doing this, dissecting their functionality. Look at the electronics, look at the sterics, because those are the two things that affect our reactions. Okay, if you're good at this, in 2 years, you might forget some of the stuff we've done here. But if you actually understand how to look at the electronics of a functional group, look at the sterics, then even if you forget some of the jargon, even if you forget some of the actual reagents, you can look at a functional group and figure out how it's going to react. How's that useful? Let's say you become a doctor. You have to prescribe a drug. Usually the reactivity comes from the functional groups of the drug. You're going to have to know a lot of drugs. My husband just throws out all these trade names of drugs. But he knows the functional groups and how they react and what puts drugs in certain classes. And he's like, that helps so much understanding organic chemistry. He's like, I never really do synthesis, but I can look at a functional group and figure out how it's likely going to react with the person. So those kinds of things is what I really try to get you to understand. And all of that's for chapter 1 in this class, pretty much. So that's what we're going to do with this functional group. We're going to dissect it. First off, a carbonyl, acetobonyl. It can behave as a nucleophile or an electrophile. So let's look at that. It has a resonance structure. Remember, we have our polarity. We have our partial positive carbon and our partial negative oxygen. It has a resonance structure, and this is a highly contributing resonance structure, though of course our neutral resonance structure is more contributing, of a carbocation with an oxygen with a negative charge. This is what makes our carbon-oxygen double bonds react so much more as electrophiles than carbon double bonds. Because carbon-carbon double bonds don't have this resonance structure because they don't have polarity. So that means that if we look at this resonance structure, and remember, our overall form is a hybrid of these two. What we see is we have a very big electron sink, meaning a place where electrons can go. And we also have a pretty big electron source. So our oxygen can act as a nucleophile because it has lone pairs and a very strong partial negative charge. Our carbon can act as an electrophile because it has a pretty strong partial positive charge. It has this resonance structure with a carbocation. So depending on what conditions we're in, it's going to direct how this is going to react. And we've already looked at these specifically for 2 reasons. We've looked at this group for a nucleophile like a Grignard reacting with it. And we've looked at this with a nucleophile with a hydride reacting with it. But we're going to look at more nucleophiles, and we're going to look at what happens if you put an electrophile in there. So we're going to look at both. Induction also agrees with our resonance structure where we have a pretty strong partial positive and partial negative charge. So both of those agree that carbon is an electrophile, but that oxygen can act as a nucleophile because it has lone pairs. So as a nucleophile, if we put in some sort of electrophile in the reaction, our oxygen can give up its electrons, and what we form is this structure, our oxygen with a positive charge with a new electrophile bond, which has this resonance structure. This is our more contributing because oxygen has a complete octet, whereas carbon doesn't here. But we can form this. So this is our carbonyl acting as a nucleophile. Our source of electrons would be the lone pairs on the oxygen. So it depends on what we're reacting this compound with. Or our carbonyl can act as an electrophile. And we've seen this reaction where the Grignard reacted. We've also seen this reaction with the hydride. But we'll look at other possible nucleophiles we can look at. And that goes through this intermediate. And our oxygen can stabilize the negative charge somewhat because oxygen is electronegative. So what we're reacting, what reagents we have in the flask is going to dictate how our carbonyl reacts. There's other things we have to note, specifically when our carbonyl is acting as an electrophile. What's the other thing we need to consider? If you look at that mechanism, we talked about electronics, the fact that we have a partial positive charge here. What's the other thing we're going to have to consider when our carbonyl acts as an electrophile? How big these groups are. Sterics can come into play depending on those R groups. So you should already be considering the difference in reactivity of an aldehyde, which has an R group and a small hydrogen, and a ketone, which has 2 R groups. But we're going to look at that steric concept in a bit more detail. So sterics does come into play, not as much as you might expect based on how we typically draw our mechanism. So the way we typically draw our mechanism, because we don't have a 3D paper, we have a 2D paper, is we often will show the nucleophile attacking under, which means if these groups are big, that's going to cause a lot of steric hindrance. But if we actually look at what experimental details suggest, sterics is still an issue, but our double bond is trigonoplanar, so we don't typically have the nucleophile come in on the same plane. Instead, the nucleophile will either attack above the plane at about a 107-degree angle, depending on the R groups, and below the plane. Which means if we form stereocenters, we're going to form both. But it also means that sterics is going to contribute, but not as much as you might think based on the way we typically draw the mechanism. Just because we don't typically try to draw the mechanism in 3D. But experimentation shows that the nucleophile actually attacks above or below the plane, not straight under, not on the same plane. So sterics is still going to be an issue, but even larger R groups, you can, if it's a strong enough nucleophile, you can still get an attack. But the less sterics, the faster the reaction, because the lower that activation energy, this transition state, isn't going to be as high of energy. So sterics does contribute, but not as much as you might think. So if we're looking at this one, our vector, of course, is A. The arrow always points towards the more electronegative atom when we're drawing those vector arrows. So considering resonance, induction, and sterics, if we're looking between a ketone and an aldehyde, and we're trying to see if our carbon is going to act more as an electrophile, if our CO bond, of course, the aldehyde is going to be a faster reaction. Aldehydes are more reactive, both because of electronics and sterics, actually. So sterics is probably a bigger issue, but electronics also contributes to the carbonyl of the aldehyde being a bit more reactive, which just means it's faster. We have more kinetics. We have less space. The hydrogen's really tiny. But electronic-wise, when we're looking at our positive charge in our transition state, here, for it to act as a nucleophile, an electrophile, our nucleophile has to attack. So we have this positive charge. The more unstable this positive charge in the resonance structure, the more likely a nucleophile is going to attack. So remember, R groups are electron donating and help stabilize that positive charge. So the more R groups you have, the more stable that carbocation, and the less likely the nucleophile is to attack. But like I said, electronics is probably not as big of an issue here. Probably sterics is causing the fact that the aldehyde is a bit more reactive. Does that mean that ketones can't react as electrophiles? No, we've already done a bunch of reactions with them. Because when we're talking about a Grignard or a hydride, we're using really, really strong nucleophiles. But if we're using weaker nucleophiles, that can definitely affect our reactivity between a ketone and an aldehyde. The nucleophiles we've looked at so far have been really strong. So we don't see as much of a difference. We've also looked a bit at this. Our carbonyl exists in equilibrium with an enol. We've looked at the enol before. But our ketone is more stable, of course, because we have a resonance structure stabilizing it. We don't have any resonance structures for a carbon-oxygen double bond because there's no polarity there. So that's one of the reasons why the ketone is more stable. That's the easiest one to explain as far as. So we've looked at the enol before. Typically the enol isn't as stable and the carbonyl predominates. Now if there's some other force that's making the enol stable, sometimes we can get it to predominate. For example, if we have a double bond here, then this double bond is in conjugation, making it more stable. Whereas the carbon-oxygen double bond would not be in conjugation. So we can make the enol exist, but it usually has to exist because something else in the molecule is making that double bond an extra stable double bond. Otherwise, we'll always get the ketone, which we've looked at before when we looked at our Markov-Nikov and anti-Markov-Nikov hydrations of the triple bond. So we can get them to exist, but typically we need resonance to make them exist. They need to be in resonance with another double bond. Of course, if we're looking at something like this structure versus this structure, clearly the enol is going to be more stable because the ketone would not be aromatic. So we clearly see that phenol exists, and that's technically an enol, even though we don't really consider it an enol because of the benzene ring. But technically, it's an alcohol directly attached to the double bond. So based on that definition, phenol is an enol. But of course, it always exists as phenol because that's a more stable double bond. So the double bond can exist, but what we typically see is the ketone. As far as solubility in water, our oxygens have hydrogen bond acceptors. We don't have any donors. We don't have any hydrogens attached to our oxygen. But they are acceptors, so we can have some water solubility of ketones and aldehydes in water. But depending on the size of the R group. So acetone and water, they bind pretty strongly. In fact, you can use acetone to dry up water in a flask really easily if you just have a small amount of drops of water, which is typically done in organic chemistry because you don't want to wipe your flask clean because that can leave little pieces of paper in your flask, and that's not good. So what we will typically do is, after we wash it, try to rinse it out. We'll rinse it out with some acetone and then blow air in it, and then the acetone evaporates really easily and it takes the water with it. So acetone will bind pretty strongly with water. It's pretty soluble. If you mix acetone and water, it will form a different layer. Because we do have that hydrogen acceptor ability. However, once we get larger R groups, we start losing water solubility. So there's only so much water solubility depending on the amount of R groups that we have. Also, boiling point, our ketones and aldehydes have dipole-dipole interactions, but they don't have hydrogen bonding ability with each other. So we typically have pretty low boiling points, bigger than, let's say, ethane, but acetone's boiling point is pretty low, just right above room temperature. So it's really easy to remove, which is nice, but it's not used as a solvent too much because we can't really heat it up. It'll boil really fast. But we use acetone all the time in the lab, so it's a very nice low boiling point solvent, but still a solvent at room temperature. Groups adjacent to our carbonyl group can affect our rate of our molecule. Electron withdrawing ligands adjacent to the carbonyl group will increase the partial positive charge on the carbon because it makes that partial positive charge more unstable. Basically, we're pulling electrons away from the partial positive charge, so that will make the carbonyl more attractive to nucleophiles because we have a less stable positive charge. Because electron, remember, a carbon that has a positive charge means it only has 6 electrons. It wants 8, so it's really unstable already. And then if we have an electron withdrawing group that's trying to take the 6 that it has away from it and pull it closer to them in the bond, that's going to make that carbonyl even more unstable because it's already electron deficient and electron withdrawing groups are trying to take it more away. What that means is a nucleophile is going to be more apt to react with it because it's more reactive. It's higher in energy. Electron donating groups typically decrease the reactivity of the carbon of the carbonyl acting as an electrophile. Now again, if we're using a strong nucleophile, it usually doesn't matter. Even if we have a bunch of OR groups, it's still going to react. But when we have a weaker nucleophile, that's really prevalent. In general, our aldehydes do oxidize easier because of sterics and electronics, just like we showed earlier. And they also undergo nucleophilic addition a bit easier because of steric hindrance. It doesn't mean we can't do it with ketones, but we're just talking about a little bit ease. We've already looked at some reactions with our hydride agents as far as when we considered reducing our carbon-oxygen double bond. This isn't new, but you still need to know this. Our H2, platinum, palladium, and nickel will reduce aldehydes and ketones because of the fact that we're catalyzing it with platinum. It's going to reduce any platinum. However, sodium borohydride and MEOH does reduce aldehydes and ketones, but it won't reduce our carbon-carbon double bonds. And of course, in the next chapter, we're going to be really looking at esters and carboxylic acids and their derivatives. And lithium aluminum hydride will reduce alkanes. Now, at this point, we haven't really talked about a reducing agent that will reduce other things and not touch the aldehyde and ketone. So we are going to address that in this chapter. Now, that we won't find a reagent that does it. Instead, we're going to protect our aldehydes and ketones. So therefore, if we protect them, then we can reduce something like a carboxylic acid or a carbon-carbon double bond and not touch our aldehyde and ketone. So we are going to talk about that. We won't really find, well, at least in this class, we won't talk about a way to reduce an aldehyde over a ketone because that's really a higher level type of protected group that we're not going to focus on here. So we already know we can take an aldehyde and further oxidize it, whereas we can't do that with a ketone. So if we have an aldehyde and we have something like our Na2Cr2O7, we can oxidize that with our chromic acid all the way to the carboxylic acid. We can also use KMnO4, which we've talked about briefly as an oxidizing agent, but typically it's so reactive with other functional groups and causes a big mess, so it's not always used. But it will also oxidize the aldehyde. But the ketones rarely oxidize further because we don't have a hydrogen there. You have to have very different types of oxidizing groups to oxidize that ketone. And again, that's a bit of what we'll be talking about in this class. If the nucleophile is strong enough to attack and not a good leaving group, then we'll get the full addition, which is what we've seen. Now, if the nucleophile is weaker and is an equal leaving group to our oxygen, then we have to consider that. So far, when we've looked at nucleophiles, we've looked at hydrides and our Grignard reagents. And neither of those, once they attack the carbon, are good leaving groups. So we've looked at the full addition to fully reduce the carbon and the oxygen bond to a single bond, typically forming alcohol. So if you recall, our nucleophile attacks, and if our nucleophile is really strong in a negative charge, then that nucleophile is going to go through this mechanism where we have a negatively charged oxygen. Then eventually water is going to come in, whether we put it in later in the reaction, which is typically the case, and then we'll get the alcohol. So the one thing to note about this is, if we forget about this part, our forward reaction is the addition, but the reversible reaction could also happen, meaning we can reform our carbon-oxygen double bond and push off the leaving group. The nucleophiles we've looked at, hydrogen and carbon, are not good leaving groups. So once we do that reaction, the reverse reaction is really unlikely. But what if we had a nucleophile like oxygen, where oxygen is an okay leaving group? Then we do have the possibility of reversibility. So we have to consider that with our nucleophile. Notice our intermediate carries a negative charge, because if we're typically talking about reacting with a very strong nucleophile, that's going to be the case. If we have a weak nucleophile, though, we have other concerns, because typically a weak nucleophile will be a good leaving group. So let's say, well, first off, typically with a weak nucleophile, we're going to have to force the reaction to occur. And oftentimes it won't occur very easily under normal conditions. So we'll often use acidic conditions to make our oxygen positive and make our carbonyl more likely to be attacked. So that'll form this oxygen with a positive charge, which is more likely to take electrons on. Then if we use a weak nucleophile, and that shouldn't have a negative charge on it, pretend like it doesn't. And typically, when we're talking about a weak nucleophile, we're looking at a neutral nucleophile. We can attack and we can get the addition. To make this reaction happen easier, we'll often use an acid catalyst. Because here's what we're comparing. Let's say we have a weak nucleophile, so a nucleophile without a charge. If this isn't done under acid catalysis, we'll get the attack and we'll form this intermediate. With a positive charge in our nucleophile and a negative charge in our oxygen. That's going to be a much higher intermediate than one that only has one positive charge, which if our nucleophile attacked neutral, it would be left with a positive charge. And then something will happen to get rid of that positive charge somewhere in the reaction, typically a proton transfer. So what we call this is activating our activating our electrophile. And activating just means we're lowering the activation energy by making this more reactive. This is pretty stable. This nucleophile is pretty stable, so it won't really react very well. They're going to be lower in energy. But if you react it with an acid and make this more unstable, it's more likely to react with that nucleophile if it's weak. So under those kinds of conditions, or under either kinds of conditions though, equilibrium is dependent on the ability of the nucleophile to function as a leaving group. So let's look at this. Let's say iodine is our nucleophile. It has a negative charge. It can attack as a nucleophile pretty easily, actually. Bromine, our halogens, they can attack as a nucleophile very easily. The problem with using a halogen in this regard is that once we get this intermediate compound, there's two things that can happen. Either we can protonate this to form the alcohol, or the lone pairs here can reform the double bond, pushing off a leaving group. But iodine is a really good leaving group. So then we have an equilibrium reaction between this forward reaction and this backwards reaction. And we need to consider that whenever we're reacting with carbon as an electrophile, because this is a good leaving group. So now instead of just a forward reaction, we have an equilibrium reaction that we have to take into account, where the backwards reaction in blue is going to be reforming the carbon-oxygen double bond. Hydrogen's not a good leaving group. Our butyl group's not a good, tert butyl group's not a good leaving group, but iodine is a great leaving group. So if we compare our nucleophiles, our carbon nucleophiles, we haven't talked about this one yet, we will. We haven't really looked at that. It's still carbon with a negative charge. We're going to look at that reagent in more detail in this chapter. But if we look at these two that we have talked about, our cyanide and our Grignard, once those attack, actually I'll just leave that. Let's say our H negative attacks. This is our intermediate. So if we were to reform the double bond, what would leave? Hydrogen isn't a good leaving group. Carbons aren't good leaving groups. So this won't happen. That would take too much energy. In theory, all reactions are reversible, But if our leaving group isn't good enough, the activation energy to do that reversible reaction is too high. So it's not going to happen. So hydrogen and carbon nucleophiles, that's typically what we have to contend with. But when we look at nucleophiles like alcohol that are okay leaving groups, then we have to consider that the reversible reaction is going to be under equilibrium. But that doesn't mean that they can't still be useful in reactions. It just means that we're going to have to consider an equilibrium, whereas when we looked at Grignards and our hydrides, we didn't. Because that backwards reaction is too unstable to happen. So we'll be looking at that in a lot of detail on Monday. And probably pretty much finish up this chapter by Wednesday, because this chapter is not very long. We talked a lot about ketones and alcohols. We're going to focus a lot more on carboxylic acids and their derivatives. Actually, we won't talk about carboxylic acids for that long either. We're going to look at the derivatives for a while. You guys have a great weekend. Don't forget, homework for electrophilic aromatic substitution is due, I think, Saturday night.
Yeah, so it's tomorrow.
So make sure you do that homework.
Have a good week.
You too.